let's just jump right in. Welcome to This Explainer. Today, we're diving into the absolute structural blueprint of modern logic itself, Euclid's elements. You know, if you've ever built a solid argument step by step, or, written a clean line of computer code, you're literally walking on the foundation laid down by the mathematical concepts we're about to explore.
Euclid essentially designed this mathematical universe as a perfectly structured game, so our explainer is going to mirror that. We'll start with the world's oldest textbook, check out the anatomy of the elements, lay down the rules of geometry, prove that very first proposition, look at the logical domino effect, and finally wrap up with his unbroken mathematical legacy.
All right, Section 1, the world's oldest textbook.
So picture this. We are traveling back to Alexandria roughly around the year 300 BCE. We're here to meet Euclid, a compiler of truly unparalleled logical vision. Now, the exact details of his life are kind of shrouded in mystery, but honestly, it doesn't matter. What he synthesized during this period fundamentally altered how humans think.
And what's really wild here is that this isn't just some dusty historical relic, it's a living, breathing document. It actually holds the distinction of being the world's oldest continuously used mathematical textbook. Think about that for a second. The exact same logical steps we are going to review today, they've been studied by ancient philosophers, Renaissance engineers, and yeah, even modern rocket scientists. It's pretty incredible.
Moving right along to Section 2, Anatomy of the Elements.
Now, to really grasp the sheer massive scale of what we're looking at, you have to realize the Elements is not just a single book about drawing triangles. Not even close. It's a vast library made up of 13 distinct books. It covers number theory in books 7 through 9, algebraic interpretations in book 2, and it even goes all the way into three-dimensional stereometry and Platonic solids in the later ones. It was basically a comprehensive master file of the entire mathematical universe known at the time.
Okay, on to Section 3, the rules of geometry.
Before we can play Euclid's game, we have to know the rules. And the biggest, most crucial restriction, you absolutely can't just pull out a ruler to measure and compare lengths. No way. Empirical proofs based on physical measurement are totally forbidden. You get exactly two tools, a straight rule with no markings on it whatsoever, and a compass. That's it. Everything, absolutely everything, has to be proven strictly through logical deduction and the inherent relationships between the shapes themselves.
So to build a universe completely from scratch, Euclid starts with the absolute simplest building block imaginable, a point. He defines it as that of which there is no part. It's a concept so infinitely small that mathematically it has zero physical dimension. It's just a pure, perfectly precise location in empty space.
Then, he takes that infinitely small point and he stretches it out. A line is defined as a length without breadth. Boom, we've just entered a one-dimensional space.
And finally, he expands that line outwards into a two-dimensional surface, defined as that which has length and breadth only. And with just those three basic definitions, Euclid has completely mapped out the flat, pristine geometric universe we are about to explore. Next up, we need the laws of physics for this new universe. Think of his 5 postulates as those absolute, undeniable physical laws. They grant us the specific ability to draw a straight line between any 2 points, extend that line continuously, draw a circle with any given center and radius, declare that all right angles are perfectly equal, and establish exactly how intersecting lines behave.
Now take those physical postulates and combine them with his 5 common notions. These are essentially the fundamental, hardwired laws of human intuition and logic. You know, things like things equal to the same thing are equal to one another, or the whole is inherently greater than the part. With our physical tools and logical rules locked in, our game board is officially set.
Let's dive right into Section 4, proving the first proposition.
All right, let's actually play the very first round of this game. The main objective of Proposition 1 is to construct a perfect equilateral triangle on a given finite straight line. And remember, we can't cheat by measuring the sides. We have to build it relying only on our permitted tools, following a highly specific, strictly logical sequence of steps.
Watch how beautifully this builds. We start with our baseline, AB. By anchoring our compass at point A, we invoke postulate 3 to draw our first circle. Now, because of how a circle is defined, every single line radiating out from that center point A to the outer edge is perfectly equal to our starting line, AB. And here's the genius part. When we repeat the exact same process, placing the compass at point B and drawing a second circle, those 2 circles naturally overlap at a point up top. Let's call that point C. If we draw straight lines connecting C down to A and C down to B, we create an unbreakable logical truth. Since line CA equals AB because of the first circle, and line CB equals AB because of the second circle, well, by common notion 1, things equal to the same thing are equal to each other. CA absolutely must equal CB. And just like that, without making a single physical measurement, we've perfectly constructed an equilateral triangle. It's brilliant!
Which brings us to section 5, the logical domino effect.
What you really need to take away from this is how proposition 1 acts like a key unlocking a massive chain reaction. Because we definitively proved that first proposition, we can now use it to mathematically prove proposition 4. This one establishes side-angle-side congruence. It proves that if two triangles share two equal sides and the angle between them is identical, their baselines have to be absolutely identical too. We literally couldn't prove this without the solid groundwork laid just a few pages prior.
And this domino effect quickly scales up into some seriously complex, beautiful proofs. Just look at proposition 5, often affectionately called the bridge of asses. Here, Euclid maps out these incredibly intricate overlapping lines to prove that the base angles of an isosceles triangle are always equal. He basically layers triangles on top of each other to forcefully drive the logic through. It's an astoundingly elegant piece of geometric machinery.
Finally, section 6, an unbroken mathematical legacy.
Now, Euclid's logical game certainly didn't stop at drawing flat shapes on a two-dimensional plane. By the time we hit Book 12, the Elements introduces something called the method of exhaustion. This was an absolutely ingenious logical tool used to calculate the relative volumes of 3D shapes, think cones, pyramids, and spheres. By packing polygons with an increasing number of sides inside a shape, they could essentially exhaust the area. Guys, this was literally an ancient precursor to modern calculus and integration.
But it's super important to remember that Euclid didn't just invent all of this out of thin air. He was the ultimate compiler. He took the brilliant, sometimes totally chaotic discoveries of earlier thinkers, like Pythagoras with number theory, Theaetetus with irrational magnitudes, and Eudoxus with the method of exhaustion. And what did he do? He bound them together. He synthesized all these disparate discoveries into a single, unbreakable logical chain that could be reliably taught, tested, and expanded upon.
So, I want to leave you with this final thought to ponder. We live in a world that is so full of shifting perspectives and subjective realities. Given that, how incredible is it that the absolute truths built from a few overlapping circles in ancient Alexandria over 2,300 years ago still completely form the bedrock of our logical universe today? I mean, without this ancient masterclass in deduction, would we even have the foundation to build modern science, engineering, or computing? Probably not. Thanks so much for exploring the elements of logic with us today.